Hello everyone, welcome to the third video of week 5. Let us return to the mortality example of the previous videos. In the previous video we have convinced ourselves that a simple linear regression model with normally distributed errors is a good model to describe the relationship between mortality rate and calcium concentration. The relationship seems to show a decrease in mortality for larger calcium concentrations. However, since the data contain uncertainty, the question is whether this is really the case or whether this graph is just merely a coincidence. In other words, can we conclude that the slope beta of the regression line is negative? Well, the estimate for beta is minus 3.2. This is clearly less than 0, but the question is whether it is extreme enough to conclude that beta is less than 0. The way to answer such a question is to test the null hypothesis beta equals 0 against the alternative beta is less than 0. Now this is a special case of testing a null hypothesis beta is equal to some pre-specified value, say beta 0. And the way to build a test statistic for this null hypothesis is similar to the construction of the test statistic for the t-test in week 4. We use a similar standardization of the estimate beta hat. We consider the difference between beta hat and beta 0 and divide this by an estimate of the standard deviation of beta hat. Now we could derive an explicit formula for the estimated standard deviation, but this goes too far here. As you will see, R automatically produces this value after we have fitted a simple linear regression model. The estimate is referred to as the standard error of beta hat, so our test statistic is the ratio of beta hat minus beta 0 divided by the standard error of beta hat. To test the null hypothesis that alpha is equal to some pre-specified value alpha 0, we use a similar test statistic. Namely, the difference between alpha hat and alpha 0 divided by the standard error of alpha hat. Now the following theorem enables us to compute p-values or critical values for both test statistics. Suppose we have a simple linear regression model for which the measurement errors are independent with a normal distribution with mean 0 and variance sigma squared. Then the standardized alpha hat and beta hat both have a t-distribution with n-2 degrees of freedom. Now this means that if we test the null hypothesis alpha equal to alpha 0, then under the null hypothesis, the test statistic has a t-distribution with n-2 degrees of freedom. And similarly, if we test the null hypothesis beta equal to beta 0, then under the null hypothesis, this test statistic for this null hypothesis also has a t-distribution with n-2 degrees of freedom. Okay, let us return to the mortality example for which we want to test the null hypothesis beta equals 0 against the alternative that it is smaller than 0. The result of this statistical test is part of the standard output that can be extracted from the fitted LM object by the function summary. Running this command produces a large summary of the fitted model. And part of the output is a table under the heading coefficients. In the first column in the table, the estimates are the estimates for the intercept and the slope, which we obtained earlier. And the second column contains the standard errors of alpha hat and beta hat. The third column is simply the ratio of column 1 divided by column 2. And this means that the third column contains the values of the test statistic for the null hypothesis alpha equal to 0 in the first row and for the null hypothesis beta equal to 0 in the second row. And finally, the fourth column contains the two-sided p-values corresponding to the observed values of the t-test statistic. Now for the null hypothesis beta equal to 0, we find the value minus 6.7 for the t-test statistic. Now this is clearly less than 0, but the question is it extreme enough? Well, the two-sided p-value is about 10 to the power minus 8. So that means that the one-sided p-value for testing against beta is less than 0 is half of this. This is still very small, so that we can safely reject the null hypothesis. That means we conclude that the slope beta is negative, so that an increase of calcium leads to a decrease in mortality. Another typical research question is the following. Suppose we increase the calcium concentration with 1 milligram per liter, then how much decrease in mortality can we expect? From the linear regression equation, we can immediately see that an increase of the x variable with 1 unit leads to a change of beta in the y variable. Now the estimate for beta is minus 3.2, so an increase of 1 in calcium concentration is estimated to lead to a decrease of about 3 in mortality rate. However, a confidence interval for beta seems to be more appropriate here. This can be determined from the standardized beta hat. Recall from the theorem that with normally distributed errors, the standardized beta hat has a t-distribution with n-2 degrees of freedom. So, this is a pivot, and the probability that it lies between plus and minus the critical value of the t-distribution at alpha over 2 is exactly equal to 1 minus alpha. Rewriting the inequality such that beta is in the middle gives the lower bound and the upper bound for a confidence interval for beta with level 1 minus alpha. Such an interval can also be extracted from the fitted LM object by means of the R function conv.int. Just applying this function to the fitted LM object gives the 95% confidence intervals for both parameters, the intercept alpha and the slope beta. For example, the 95% confidence interval for alpha is roughly from 1618 to 1735, which would correspond to the mortality rate at 0 calcium concentration. Now suppose we want a 99% confidence interval for only the slope. Well, then one has to specify that this concerns the parameter corresponding to the variable calcium, and one has to adjust the level of the confidence interval. We find that an increase of 1 milligram per liter of calcium concentration leads to a decrease of about 2 to 5 in mortality. Now finally, another research question is the following. Given calcium concentration 65 milligrams per liter, can you predict the corresponding mortality rate? Of course, one could do this simply by hand using the least squares estimates. This can be done by extracting the estimates from the fitted LM object and computing the value of alpha hat plus beta hat times 65. We find that at calcium concentration 65, mortality is predicted to be about 1467. On the other hand, this can also be extracted from the LM object by means of the function predict. In the call, one has to specify the value 65 for calcium in the option new data, and this must be done by means of a data frame containing the variable calcium with value 65. Running this call also gives the estimated mortality at calcium concentration 65. The nice thing about this method is that by simply adding confidence for the option interval, the R function predict also returns the lower and upper bound of a confidence interval. By default, the level is 95%, but this can be changed by means of the option level. Running this call, R returns the point estimate and the lower and upper bounds of the 90% confidence interval for the expected mortality at calcium concentration 65. One last remark. In the output of summary, you may have noticed that the p-values for testing beta equal to 0 and the one corresponding to what is called the F statistic are exactly the same. This has to do with the fact that the simple linear regression model is a special case of a multiple linear regression model. In the simple linear regression model, we have just one x variable, whereas in the multiple linear regression model, we may have more than one x variable. With just one x variable, the t-test for beta is equivalent to what is called the f-test. Both testing problems are different when more than one x variable participate in the linear regression model. Well, this will be the topic of the next video. See you then.